Hello there, everybody. Welcome back to Chem Complete. Professor Tomney here, and I am going to take a look at another hydration reaction for alkenes today. And this particular one is the Oxymercuration Demercuration reaction for alkenes, which will turn the pi bond into a hydroxyl group or an alcohol functional group. So we are going to take a look at all the specifics for this reaction coming up on the channel right now. All right, so just a quick reminder before we get started here. If you go to chemcomplete.com, there's lots of free resources for your learning that we're constantly updating. And there are also very affordable guides if you are stuck on a specific subject. It's a great way to support the channel. So on to the oxymercuration demercuration of alkenes. So this is a hydration reaction of alkenes. Hydration meaning water. And we are going to add a sum total of water, H2O, across the alkene double bond in this process throughout different steps. So oxymercuration demercuration is typically used in smaller lab settings. You can achieve a hydration reaction using strong acids as well as high temperatures. This usually scales up pretty well with industrial types of glassware or settings. However, in smaller labs, it avoids higher temperatures and it avoids the need for very potent, strong acids such as H2SO4 or something like that. Okay, now the alkenes in this reaction are going to be treated with mercury to acetate. So that is a mercury metal that is going to have two acetate groups that are on both sides or either side of the mercury there. And this is typically run in aqueous THF solvent. So the THF also has water present. And just a reminder, if you saw the hydroboration lecture, THF is tetrahydrofuran. It is a solvent that is used in lots of different organic reactions. It's an ether-based solvent. Okay, and when this occurs, it's going to yield a mercurinium ion. So if you've seen the bromonium ion that forms in the Br2 addition for an alkene, this is going to be very similar. You're going to get essentially what amounts to a three-membered ring that's going to have the mercury ion kind of wedged or stuck in the middle there. So let's take a look at just some of the basics here. So as far as the reagent itself, we have the mercury. And the mercury is going to have two acetate groups. Now, what is an acetate group? You've got this oxygen. It's a C double bond O, so a carbonyl. And then you've got a CH3. Okay, so kind of like we see this portionality in acetic acid, the acetyl group is just the one methyl group coming off of that carbonyl there. So we're going to have a second one that would look identical, right? So this is really the reagent that we're looking at. And again, if you take a look at the text above there, it is typically going to be abbreviated as HGOAC2. That's how you're going to see it written over the arrows when we're dealing with organic synthesis. So this chunk right here is going to be one of your O acetyl groups, right? So you've got that there. Plus, we've got our, what we're going to start with is just a generic alkene. And then we'll get more specific when we talk about the outcomes here. So if you put these together in the aqueous tetrahydrofuran, what you're going to end up with is the three-membered intermediate state. Okay, so the carbon here, or the carbon-carbon pi bond, I should say, has broken apart, right? And then in between here is going to be a mercury ion. It's got a positive charge, okay, and then it still has one of the two acetyl groups that's left there, all right, and that would be the first intermediate that we would have there. So that mercury is really wedged between the two. It's making a three-membered ring right there. And so we know that this is our alkene here, and then this is the intermediate that was mentioned above, okay. This is going to be the mercurinium ion. And that is really the first and one of the important steps in this reaction, because this is going to control some of the stereochemistry we see at the end here. All right, now in this process, because we do have H2O present in the THF, water being present in solution is going to be able to come in and attack this ion. It's a pretty reactive ion given the size of mercury and the angle strain of a three-membered ring there. So water will open the mercurinium intermediate up, and it will essentially add a H2O group onto one of the two carbons, and then the other carbon will have a remaining mercury with an acetate group on it. Okay, so the intermediate that results from that is then going to be an organomercury compound, and that will be treated with a secondary step. So it's a separate step that comes after with sodium borohydride, which is a reducing agent. The NaBH4 is in the second step. Okay, now when we do this, what you're going to essentially see is you've got the carbon with the carbon, and we're going to really focus on the attack here for the mercury. Okay, it's going to attack one of the carbons involved. Now, it turns out it will attack the more substituted carbon, and we'll take a look at that in a minute. All right, but what we've got here is that the water is going to come in. Don't forget that's positive. Okay, and it will attack, we'll just attack the nearest carbon here, right? So when it attacks one of these carbons that's got a partial positive buildup going on, it's going to then release these electrons back to the mercury in that process. And so what we end up with when we do this, now there's another step we're going to look at in the mechanism that I'm not showing here at the moment, is that we will get the mercury now isolated to just one of the carbons. Its charge has gone away because it received some of those electrons back when that three-membered ring broke open. And then on the other corresponding carbon, right, we would have a hydrogen here because that water needed to come in from the back. So the step I'm not showing is the deprotonation of the water. I'm taking it straight to an alcohol here, but we'll take a look at that in a couple of minutes. And then the secondary step after this has occurred is that we're going to treat it with the NaBH4. And when we treat it with the NaBH4, it's going to reduce at this step, and it will bring this compound into the state where you've got now just a hydrogen. I'm actually going to make that my wedge there. Okay, a hydrogen that takes the place of the organomercury portionality. And then you would still have your OH here. Now notice that the OH, okay, is in back here, and the H is in the front there. So that is important, and you can follow that along backwards here, okay? This is going to be important in the stereochemical outcomes that we always see for this reaction. It must proceed in this way because the water must attack on a opposite side of that large intermediate. The mercury is too sterically hindering in that three-membered ring. And again, if you've seen anything related to the Br2 addition to alkenes with the bromonium ion, this is very, very similar from a mechanistic standpoint. All right, now, what's important to notice here is even though we had partial positives that were building up, we did not have a carbocation present in this reaction. Okay, so no carbocation in the mechanism means that we will get specific regiochemistry and stereochemistry outcomes, and you can see them listed here. So the regiochemistry, which again is focused on the region in which this alcohol is going to add, is Markovinkov addition of the hydroxyl group. So what that means is the more substituted position, if we're talking about primary, secondary, tertiary, and so on, the more substituted position will be the position that takes on that hydroxyl group. And from a stereochemistry perspective, the orientation will always be 100% anti-addition. Okay, and that is because they will always appear on opposite sides of the carbon-carbon bond, or what was originally the carbon-carbon double bond, right, has gone down to a single sigma bond at this point. But they will always be on the opposite faces of the molecule when we're looking at them. And so this is very important because it is going to have very specific consequences when we are considering what we are trying to get out of this reaction. So if I were to draw just a simple example here, okay, and then I were to expose this to the reagent set. So number one, I would need my HgOAc2. And again, that would be in water with THF. And then the second step would be a subsequent treating with the sodium borohydride reagent. So when I do this, the final result would be that I am going to have the hydroxyl group adding to the more substituted of these two. Well, if I take a look at them, this one right here is a tertiary position, whereas this one down here is a secondary position. So Markovinkov addition means that it goes to the more substituted position. So I will have the OH group over here on this carbon. Okay, so then as a corresponding result, that means that I would have on the opposite carbon, or the opposite side, that hydrogen after the NABH4 is used. So this was originally the position of the organomercury intermediate, and it is now just the hydrogen here. Okay, so again, it is important to note that we have 100% anti-addition, meaning that they are going on opposite sides of the molecule, or opposite face of the molecule, and that the OH is always adding to this tertiary position in this case instead of the secondary position. So that accounts for the regiochemistry, the Markovinkov addition, as well as the stereochemistry being 100% anti-addition. All right, so to wrap this up, let's take one official run through or look at the mechanism and what we would be working with here. Okay, and we want to use something that can kind of differentiate the regiochemistry when we're looking at it here. So we'll go ahead and we'll make a 5-membered ring. Okay, and with this, we'll go ahead and we'll add the double bond here. And then let's put a methyl group here because we need to differentiate. We need a more substituted position to help show this. All right, so the first step when we get the mercury acetate reagent, which I'm going to draw out here again to some degree. Okay, I'll just put these as OAC groups to help save a little bit of time here. Okay. What we are going to have is that one of these acetyl groups will leave. It's resonance stabilized. It will very readily go into solution. But as that happens, you're going to get the pi electrons reaching out to the mercury, which would be starting to build up positive charge. And that mercury does have some electron property to it, being that it's one of the larger transition metals. Okay, and that's going to be able to send that right back here. And so we get the 3-membered intermediate that we are familiar with at this point. So for the first step, we get the mercurinium ion. And I am drawing it wedged each time. It could also be dashed. So do note that you could get both wedged and dashed versions, which if there are chiral centers in your potential organic reagent, that could lead to racemic mixtures at the end of the day when you're doing your workup here. All right, so there is our intermediate, and we don't want to forget that there is a methyl group that we're working with down here. All right, so at this point, the water would come in and would attack. So here's the water. It's going to attack the more substituted position because, again, this is tertiary. It's Markovinkov. Now, it attacks this because as the mercury gets ready to break open, right, it has to break open one way or the other. It's going to start breaking open at the tertiary site because partial positive charge is going to form wherever it starts to break. Well, similar to carbocations, even though this is not one, you want the partial positive charge to be stabilized in the tertiary position instead of the secondary position. So these electrons will go to the mercury, and that will effectively break open this intermediate 3-membered ring and allow us to proceed forward to the next step. So the next step, we have to deal with the fact that this water has come in a protonated form. So this was what I mentioned a minute ago where I said there's an extra step here, but I'm just drawing the alcohol. So now we're going to go ahead and we're going to take care of that. All right, so if we take a look at this, we now have the mercury up here in this position because it was let go of from the more substituted position. It still has the acetyl group. There would be a hydrogen back here. And then over here, we would have the methyl group, which has now been pushed over here to the front due to that water attacking in the back to get away from the mercurinium ion. And then in the back, where the water did attach, we would have water. So you're going to have the H2O just like this. It doesn't come as an alcohol. There's an additional step here, and that oxygen has a positive charge on it. Okay, so what we did release, if you come and you look back here, we released an O-acetyl group, which can act effectively as a base here to help get rid of this. Okay, so the O-acetyl group will come and grab one of these hydrogens, and then you can send some of these electrons back to the oxygen, which will effectively create your alcohol that you're looking for, right? So then in the next step, we need to finally start dealing with the mercury portionality. So what do we have now? We've got the 5-membered ring, and the 5-membered ring now has an alcohol in this back position. There's a methyl group in this front position. And then if we take a look here, right, we've still got the mercury acetate portionality, and we still have the hydrogen. All right. So from here, this is the last step. Now, in a regular organic course that I would be teaching, I kind of just allow students to write this step into the mechanism. The actual mechanism behind it is proposed to be a radical mechanism. So you get the hydride. The hydride will end up undergoing a radical type of cleaving or mechanism with the mercury group, and then that will return mercury metal to you. So unless you were in kind of a more advanced synthetic mechanistic course, like a graduate level course, I wouldn't necessarily expect most teachers, even some of the books kind of just, mention it and then move on from there. So you've got your, I don't like that angle. You've got your NaBH4, right? And that's going to take care of the hydrogen in place of the mercury here. So now the final result would be that I've got 2 hydrogens here, and then I would have the CH3 here, and I would have the OH down here. Okay, so again, 100% anti in the stereochemistry, and we also get regiochemically speaking the hydroxyl added to this tertiary position. Okay, and then if you wanted to down here, you could write plus mercury metal, because that would be released at the end of this reaction and is something you would have to consider. All right, so that pretty much takes care of the oxymercuration mechanism and all of the details. So I hope you found this useful. Again, if you head on over to chemcomplete.com, there's lots of resources over there that can help you with your studies, and it is a great way to support the channel. It's very, very affordable to buy some of the guides that we have over there that will give you more details than your class notes could ever. So I hope you learned something today. Thank you so much for choosing to learn with Chem Complete. If you like, comment, subscribe, I will try to get back to you, interact with you, and it will keep you up to date as you go through your chemistry travels and new content is released. So thank you so much for learning with me, and I will see everybody in the next lecture.